I'm Sean Azimi. I'm the Principal Technologist for Robotics at NASA's Space Technology Mission Directorate. And I'd like to introduce our next speaker. So Deborah mentioned that there is, we have a couple speakers today, one representing an ongoing technology development project. So it's Ryan McCormick, the project manager and principal investigator for the Cold Operable Lunar Deployable Arm, or COLDArm, at NASA JPL. COLDArm is an STMV-funded technology demonstration project for a robotic arm that integrates both metallic glass gear technology into a robot that will have the capability to operate at very low temperatures, such as those found in a permanently shadowed region without the need for survival heaters. It's planned for a CLIPS flight and lunar surface demo, and I'll let Ryan get into the details since he's got his charts up. With that, take it away, Ryan.
Hi, thanks, Sean. I am Ryan McCormick from JPL, and I'm the project manager for COLDArm, which is Cold Operable Lunar Deployable Arm. So just to give a quick overview, the project is funded under LSII, and it's managed through STMV's Game Changing Development Program. It was originally funded as a ground demonstration with potential path to a CLIPS launch, and then the scope was increased to include lander integration and surface operations for a lunar tech demo, and so it'll be a tailored 7120.8. We're pre-manifested on a 2024 flight PRISM 1B to Schrodinger Basin, and the primary focus of this is to demonstrate operation of a cryogenic capable robotic manipulator on the lunar surface. So a quick overview of the arm. Our industrial partner on this is Motive Space Systems. The arm will look very similar to the Phoenix and Insight arm. So it'll be 4 degrees of freedom, roughly 2 meters in length. The initial reference experiment we're doing right now uses a 3D printed scoop to collect geotechnical properties, and we'll have roughly 40 newtons of tip force in the primary workspace, which is the same requirement as needed for Phoenix. The main innovation is that we can do cold operation without heaters below 100 Kelvin. This is done through the bulk metallic glass actuators and harmonic flex blinds, in addition to cold motor controllers. On the surface, we also have a robotic avionics and sensor kit. These will be in a warm electronics box here, and this largely leverages the Mars helicopter avionics, which is successfully flying on Mars, including the cameras. And additionally, there will be a six-axis force torque sensor at the wrist. So just overall, again, the main goal is to demonstrate that the COLDArm can operate in a cryogenic lunar environment with capabilities supporting future planetary and lunar exploration. So our first objective is to demonstrate the arm on the lunar surface. The second objective is to demonstrate these key technologies in the relevant environments without active heaters. Objective 3 is to perform a NASA-defined experiment with a robotic arm for the lunar exploration. So while the main focus is to show demonstration of the arm and demonstrate these cold technologies, we want to do some opportunistic experiments while we're there, and then also demonstrate risk reduction for future planetary and lunar exploration. For the demonstrators and qualifications, a lot of the V&V will be done here on Earth, so we can use TVAC chambers and cold chambers at various levels of the component all the way up to assembly. We'll flight qualify the overall system, and then we'll do the lunar demonstration, which will bring together the combinations of gravity, dust, environment, radiation, and temperature that are hard to simulate on the Earth. Some of the component level testing we've demonstrated for the key components. So this is some flex splines for bulk metallic glass. This is a cross section of the cold motor controller. So these will all be integrated into a payload. So this is a more representative view of it. So you can see kind of the bluish gray base plate. The idea is everything will be mounted onto a single base plate for easier integration to the lander. And then this will go to the overall lunar demonstration. For an overall system diagram, so JPL is providing the end effector, the robotic avionics and sensor kit, and the bulk metallic glass gear motors and harmonics. And then Motive is providing the Daitsu motor controllers, and they'll do the robotic arm design, including arm structure, launch locks, actuators, and base plate. So they'll integrate all of this and deliver back to JPL for final testing before we go and do lander integration. So a quick overall schedule for what we're aiming to. We're currently aiming to complete everything and be ready to bolt on by the end of FY22, so about a year from now. And this will give us time for an FY24 flight. These future dates may shift some, but right now we're planning to be ready to bolt on by the end of next fiscal year. Here's a quick reference experiment for something we could do. The final experiment is still being decided on. But this would take, after we land, we would take images of the surface. We would then deploy the arm and do robotic arm checkouts. And then the scoop is, it has different bearing plates on them, so 2 different sizes. And so this would push one bearing plate into the surface. It would then rotate around and then push the second bearing plate into the surface. We can measure displacement force with the force torque sensor. We also have the capability of doing a surface shear test with another set of features on the scoop. And then we can demonstrate trenching and bring the sample back to the cameras and scoop them out to get information like angle of repose. Right now, the scoop, we're working with Marshall on the 3D printing, and then we're working with both Kennedy and Glenn on the various features we're attaching to this scoop. But the idea is it will be 3D printed under the new NASA standard 6030 for additive manufacturing. After this is completed, we'll position the elbow, so it will be as shadowed as possible, and then we'll wait for after dusk so we can demonstrate a robotic motion as cold as we can possibly get, resources permitting, from the lander. So here's just a quick 1-minute video of the overall scoop testing. So this is sped up, so just showing excavation and lunar simulant. Then after this, we'll do the pressure sinkage. So you have one surface area, we'll push down and measure forces. We'll push down a second face and measure forces. And then we also have features to do a shear test with. So we'll push along the surface and then drag. And so this was a quick prototype we made with an existing arm we already had. So the final version will be slightly different. So the first key technology is molten taut glass. So gears. So this is a planetary gear motor. So you can see it spinning here. So instead of a crystalline structure that it's an amorphous metal, this is showing a harmonic flex spline and a harmonic gear set that's been cooled with liquid nitrogen. This is a cool video here where we put the gear motor in LN2. We turned off all the Hall sensors to get steady state temperature, and then we're able to operate the motor in liquid nitrogen. We were then able to pull it out, set it on the table, so you had huge temperature gradients as things were heating at different rates, and we're still able to operate it. A lot of the testing is done down at SwampWorks at KSC. They can do dyno below 100 Kelvin. And then we did cryogenic shock testing, which also got a tweet from the NASA administrator. The other one is the JC motor controller from Motive. This was developed through an SBIR. The commercial spaceflight version has previously flown on a NASA mission and is being developed into a few missions, which may have already been delivered for some of these. So they've demonstrated all the critical technology or critical capabilities below -1 ADC. And there's a few auxiliary functions they're still working on, but we're confident we'll have those by the time we need to deliver. So aside from just this first mission, the idea is we can feed into future missions. So for example, the geotechnical property experiment can give information for landers, rovers, ISRU, or humans. This potentially could just be a standard engineering asset for future CLIPS missions. We're part of the Intrepid rover study. We're talking with the Lunar terrain vehicle folks And then the individual technologies can be used outside of robotic arms, so maybe use them in rovers, gimbals for exploring lunar night and PSRs, and then show various levels of autonomy. Looking for Mars, we could do things like long-range rovers or areas like Ocean World, like Europa Lander or Enceladus Sample. We are working on a tool changer concept. So the idea is we could have multiple payloads that we could swap out on the surface. And so we would provide power and comms and mechanical interfaces to each of these. It's part of a NASA at Work challenge and then a Honey, I Shrunk the Payloads external challenge. Common payload interface was developed, and the idea is these could both be used for the COLDArm project or the Cadre project. So this ICD went out for these various challenges, but something like this is what we plan to use in the future. We are looking at increasing this to about a U and a kilogram payload. The idea is we would use a similar bolted interface to this and just have a standard interface we have experience with. And then also we did have a payload user's guide, which was developed as part of this, which defined a lot of the other information that would be needed for future payloads. Okay. Any questions?
There might have been a couple in the chat.
Okay.
Thank you very much for that talk, Ryan. I think if, well, we have a couple minutes, so why don't we go ahead. So one question was, why develop a cold arm when low-grade heat can be supplied by radioisotopes or by our integrated solution?
So I know there's some restrictions on radioisotopes. There are other, for at least some of these missions, other examples would be if you're trying to collect volatiles, you don't want heat around your collection point. And so this moves the heat away from those areas. And I'm not sure what the integrated solution is.
Yep, yeah, and you can, it's from the New Frontier Technology Group.
Okay.
And then let's see. Leslie Gertz said the video showed testing in non-consolidated regolith simulant. The behaviors of dry consolidated and icy consolidated regolith will be significantly different, and the tool is presumably intended for all three situations. Are such tests being planned?
So that was more of a proof of concept testing, and we're still working on our final test plan for the final versions of these. So we're still working at that. So those are things we're considering for the final testing.
Great, thanks. And then one last question from Carol Stoker. Do the moving parts in the motors require lubrication? And if so, what lubricant is used?
So we're going to use dry lubricants for them. And so they won't have wet lubricants that need to be heated, and they won't have any concern with dripping out or anything.
Excellent.
But right now we're planning to do dry lubricants.
Great. And then there's one more invitation to continue a conversation in the chat. So go ahead and take a look there when you have a chance.
Okay.
Yeah, in addition to other questions, which we will have a half-hour discussion period at the end of the day as well. So if there's further discussion that everybody wants to have, we can have it at that time. All right. With that, let's transition to our next talk.